the universe. From the glowing wisps of nebula to the shine of newborn stars, from blazing galaxies to the warm embrace of our own sun, the universe has dazzled humanity for all time with its brilliance. However, the universe is mostly space, and that space is cold, very cold. But that doesn't mean there isn't anything to see. When observed in a special way, even cold things glow. Like these strangely colored blobs, they aren't exotic cosmic objects at all, nor will they ever fill a room with their light. Even these ice cubes emit radiation we can detect, infrared radiation. Infrared radiation is created by the motion of atoms and molecules that are in matter. So even objects that we think of as being very cold, such as ice cubes, emit radiation. Like ice cubes, the coldest things in space emit radiation. And with special instruments, we can detect this radiation to reveal a dazzling universe of unseen wonders. Legions of galaxies and what lies within their cores. The secrets of seemingly empty space. The birthplace of stars. And even the birthplace of planets. Planets like ours. How do we see these things? With the Spitzer Space Telescope, the last of the 4 great observatories. Spitzer's greatness is not due to its size. With a mirror less than 3 feet across, it is easily dwarfed by the other great observatories, Hubble and Chandra. But despite its modest stature, Spitzer's infrared observations are 1,000 times more sensitive than any ever made. That's because it does its work in the frigid depths of space. Positioned in a unique orbit, 1,000,000 miles distant, Spitzer trails the Earth like a lone sentinel, following us as we journey around the sun. Here, in the deep freeze of space, Spitzer is far from anything that would interfere with its infrared vision. By gazing into the distant reaches of space-time, or perhaps somewhere nearby in our own galaxy, photons are gathered by Spitzer's mirror. From here, the photons can be directed to different instruments that are frozen in liquid helium so they don't emit infrared radiation that would interfere with the observations. With a photometer, spectrometer, and cameras, observers can count, characterize, and make images with the infrared energy from sources, allowing us to see what has never been known. They can see stars that are invisible to our vision. They can sense vast, invisible clouds of matter and reveal what they're made of. They can reveal dust around stars, dust that is forming planets like ours. And they can detect galaxies in the deepest reaches of space-time.
Main engine start and liftoff of the Delta II.
Launched in August of 2003, Spitzer has completed its primary mission: to establish a legacy of new information about our universe, the Spitzer legacy. How do stars form? What causes them to form? How do solar systems form? Do all stars have solar systems? Are there any solar systems like ours? Are there many? Are there few? What does our galaxy really look like? Are new stars forming in our galaxy? Where? Why did galaxies form? Were the first galaxies like our galaxy? Why are galaxies where they are? How did the structure of the universe form? These are questions that the Spitzer Legacy Program is designed to address. Using Spitzer's unprecedented infrared vision, 6 programs focused on different aspects to fill gaps in our knowledge. The SWIRE survey addresses what is perhaps the biggest story of Spitzer's first legacy missions. This infrared image made by the SWIRE survey contains over 500,000 brilliant gleaming sources. It covers more area than 36 full moons. In astronomical terms, a gigantic swath of sky. Yet this image is only one of 6 fields that together cover an area larger than 250 full moons. Look closer, and the enormity of this single image becomes apparent. Vast numbers of what first appear to be pinpoints of light are not what they seem. The pinpoints are entire galaxies, seemingly innumerable. By virtue of this wide coverage, SWIRE is helping to piece together one of the biggest subjects in astronomy: the large-scale structure of the universe, and how galaxies evolved within that structure. This image covers the same area as the SWIRE image, but it looks much different. It is a simulation of structure in the universe, showing the distribution of matter that makes stars and galaxies. With the information that SWIRE is providing, astronomers hope to put the 2 pictures together and finally understand a true picture of cosmic structure and how galaxies evolved within it.
SWIRE looked at 6 separate fields on the sky, that is 6 separate directions at high galactic latitudes. And the reason for that is that we wanted to look out of the plane of the galaxy. And since we're sitting in the plane of the galaxy, we're sitting in the middle of a lot of interstellar material which blocks our view of the extragalactic sky. So we looked up above the plane of the galaxy and out through the higher regions where there's very little interstellar material between us and the external galaxies. And we picked 6 fields around the sky that have exceptionally low amounts of interstellar material between us and them. And all told, we observed about 50 square degrees, and that's about equivalent to the area covered by about 250 full moons. So one of the key reasons that we wanted to look at large areas of the sky is that we wanted to have within the same field of view, we wanted to cover the area of a lot of the largest structures that exist in the universe. The largest ones we know about stretch over significant areas of the sky as you look at it. And so we needed to block out large footprints on the sky, if you like, so that we can cover all of them and see all of the different environments that galaxies live in, all in one contiguous area. Another reason that we wanted to observe large areas of the sky is just to see lots of different objects and have enough of them so that we could accumulate the statistics on their nature, all in the same areas of sky. Spitzer has 3 main instruments, and we used 2 of those for our imaging survey. We used the 2 instruments that have imaging arrays, that is, we basically just took images of the sky in all of the bands available to those 2 different instruments. The 2 instruments are the infrared array camera, which works in the shorter wavelength bands, and then the other instrument that works in the longer wavelength region is called MIPS, the multiband imaging photometer, which has 3 wavelength regions, and we observed in all 3 of those as well for a total of 7 bands. So we wanted to use all of those 7 wavelength regions because each one is sensitive to different emission mechanisms from the galaxies that we're looking for. At the shorter wavelengths, we can see chiefly the light from the stars themselves, the starlight, and they shine most brightly in the shorter wavelength bands that the infrared array camera is sensitive to. And in addition, we wanted to, at the same time, in the same regions of sky, detect the light from the interstellar material that lies between the stars. And it chiefly emits at longer wavelengths, and so we wanted the longer wavelength camera to image the sky at the same time. The primary goal for SWIRE is to understand galaxy evolution, and we decided we needed to look at large fields because we wanted to look at the evolution of different types of galaxies together in the same volume of space. We didn't want to zoom in on one kind of galaxy over here and a different kind of galaxy over there. And in particular, we wanted to trace those galaxies over the cosmic web. The cosmic web is the filaments and clusters and voids, the patterns of galaxies as we find them in the universe. They've been mapped very well in the local universe, but not so well in the distant universe at all. And so by taking SWIRE and looking deep into the universe in large patches of sky, we could actually see how things are forming at moderate distances away from the Earth. One of the key issues is that we don't understand the relationship between the cold dark matter that we suspect lies out there tracing the major structures in space and the way that the galaxies have formed within the concentrations of this dark matter. Now, cold dark matter is one of the strangest concepts we actually have. If you look up at the night sky, you see the stars shining brightly and you think the universe is dominated by these wonderful points of light, and then the galaxies that are agglomerations of stars which shine brightly. But in fact, to our astonishment, we learned that only about 4% of the matter in the entire universe is actually visible, whether through the naked eye or the telescope. We've learned this by detecting the gravity of large amounts of additional matter that we can't see with our eyes, but we can just detect its effect by its gravitational pull on the visible matter. And in fact, astronomers believe that about 20% of the rest of the matter in the universe is what we call this cold dark matter, and it dominates the gravitational behavior of what we see, the galaxies, the light elements. And so we can look for the galaxies and we can trace out their structures on the sky, and that's what we're trying to do with SWIRE. And we're hoping that it will highlight the dark matter that lies underneath that we can't see. The way that SWIRE is going to study the evolution of galaxies is what we want to do is compare how the distant universe looks to the local universe. Astronomy has this fabulous aspect to it that we can use it as a time machine. Because light takes a finite amount of time to travel, the further away an object is, the further back in time you're actually looking back to see it at. And so if we just look across the solar system, we're looking at the distance of a few light hours. But if we look outside to the Andromeda Nebula, which is our nearest neighbor large spiral galaxy, that's about 2 million years. So we're seeing Andromeda as it was 2 million years ago. Now, if we just keep on looking further and further away back into the past of the universe, we can see how galaxies actually appeared a long time ago. We just look further away and there it is. And so SWIRE is looking back large distances, a range of distances, up to several billion light years ago, just by looking far enough away into our deep field images to see the galaxies how they looked before. So we will measure how they appeared in the past, and then we will compare them to objects that we know and love in our local universe. For example, a beautiful spiral galaxy such as the Whirlpool, we can look in detail at it in the local universe and then look back at some distant examples and try to see how its predecessors might have looked far back in the past. Again, another example in the local universe, we might look at the beautiful active radio galaxy Centaurus A, which we can see in glorious detail locally, and then look back to see what kind of objects were like it or might have evolved into it in the distant universe by using this wonderful light travel time machine. SWIRE has an interesting technique for identifying different kinds of galaxies in the distant universe and comparing them to the local universe. In fact, it's a technique that Spitzer as a whole uses and in fact was partly designed to do. Now, different kinds of galaxies emit in different proportions in the different wavelength regions that Spitzer can observe with. So in the shorter wavelength instrument, the IRAC camera has 4 bands which are very sensitive to the light from old stars, and that's true both in the local universe and in the distant universe, whereas the MIPS instrument, the longer wavelength one, is sensitive to the re-radiated light from dust, that is when stars are mixed with interstellar material, they can heat up the dust, and then that dust emits light. And we can see that idea by looking at what we call the spectral energy distribution of a galaxy. If we plot the energy coming out in those different wavelength regions, we can get some idea of what a galaxy looks like, and that works both in the local universe and the distant universe, and we can compare well-studied objects locally to those in the distant universe to get an idea of the relative proportions of galaxies. And we have to fold into that the fact that the galaxies in the distant universe are redshifted compared to the local ones, and so their spectral energy distributions actually come out at a slightly longer wavelength than in the local universe. And that is actually a nice feature because we can use the shift to give us an estimate of the distance of that object. And we can explore these ideas if we look at this illustration here. So on this plot here, what we're looking at is along the bottom axis we have the wavelength range going all the way from optical wavelengths here out into the very far infrared over here. If we look first in this top panel up here, we have a star-forming galaxy. And the black line shows the spectral energy distribution of a well-known local object which has a huge amount of star formation currently going on, but also has the light from the already existing evolved stellar population still very visible, and that's shown here by this bump that we see in the black line. That's actually the emission in the near-infrared wavelength region from the old stars that exist, that dominate the starlight of the galaxy. And then in addition we have this excess of emission here, very strong and bright component. This is actually produced by the interstellar material, which is being heated up by young stars as they form in clouds of gas and dust. Down here in the bottom two panels we have some very different objects. These are active galaxies, or quasars, where there's a massive black hole embedded in the object. And in fact the light from this quasar is so bright it's completely overwhelming any light from stars. Now there's another class of galaxy that we are looking at with SWIRE that's important to recognize, and it can also be determined from the general shape of its spectral energy distribution, such as those we've just been looking at, is an elliptical galaxy. And it differs from the two that I've shown you in that it does not have much radiation at all in the longer wavelength bands. The energy just keeps on falling off and into the infrared because there is essentially not much interstellar material in these objects and no ongoing star formation, so we just see the old stellar light. Now the difference between these different spectral energy distributions that we've been talking about is how we are able to determine what kinds of galaxies we're looking at the distant universe too. So now if we look again at this figure, and instead of concentrating now on the black line, which is the illustration of one of our local objects, but instead we look at the red points. These are some Spitzer measurements of an actual distant object that we've discovered in one of our fields. And what we can do is we can look at this general shape and try to compare it to one of the spectral energy distributions that we have from objects in our local universe, and by comparison make a judgment as to what kind of object it is we're looking at. Moreover, because of the expansion of the universe and the consequent redshifting of objects within it, we can use that to get an estimate of how far away the object is. What we do is we take the spectral energy distribution, the black line, where it starts out in our local universe, and then we slide it to the right until we get a match to the Spitzer object. And when these points line up nicely with this peak that we see in our local template, then we have a good match both to the kind of object we're looking at and an approximate estimate of how far away it is. So you can see that using this technique we can do two things at once. We can get a good characterization of the kind of object we're looking at from the general overall spectral shape, and we can also use the amount of redshift that we had to apply to the local template to get an estimate of the approximate distance of this object in the universe. So what we're doing with this technique is trying to discover the differences in detail in the evolutionary history of galaxies at the earlier epochs and compared to how the universe appears today. And so what we can do is we can map out the structure of these different kinds of galaxies across the large areas of space that we're investigating. We can look for clusters, we can look for filaments, we can look for areas without any of these kinds of galaxies, and we can compare how the active galaxies, the quasars, look with regard to their structure on the sky to the actively star-forming galaxies and to the evolved ellipticals, which don't have any star formation going on at all. Well, so far we've found some very tantalizing new results from these investigations. It was known previously that both star-forming galaxies and quasars had a much higher peak in their activity in the early epochs of the universe than they do now. But SWIRE has begun to map these out in detail. And one of the first things we've discovered that the very brightest objects seem to be dominated by quasar light. But as we drop down just a little bit in brightness, we find lots and lots and lots of very luminous star-forming galaxies. And they tend to dominate the Spitzer samples very strongly when we map them out on the sky. We are also finding some evidence that these highly luminous star-forming, actively star-forming galaxies are highly clustered. That is, they might inhabit the most dense regions of the universe at these epochs. And we're talking about distances or look-back times of 5 to 7 billion years ago. What we're discovering with SWIRE will contribute to our overall understanding of how galaxies formed and how the large structures that we find galaxies in today came together. What we're discovering is the star formation rates that were going on at early times in some of the most massive galaxies as a function of where those galaxies lie within the large-scale structures that we see. And we're also tying into that the quasar activity. We think that the growth of galaxies is very closely tied to the growth of the black holes inside of galaxies, and we're able to map that directly by using these techniques to distinguish these two different kinds of galaxies and see how they actually coexist in space at these epochs a long time ago. So the ultimate goal of SWIRE is to be able to map these structures out on the sky, delineated by the different galaxy types, and not only in 2 dimensions, that is a map on the sky of filaments and clusters and voids, but in 3 dimensions. And so we'll have a volume of the sky at these moderate to distant distances in the universe where we've actually mapped the distribution of the different types of galaxies. And ultimately, we hope to compare that to what is seen in the local universe in some of the large-scale surveys that have been done in recent years, such as the Sloan Digital Sky Survey, which has actually taken a huge amount of effort to map the entire northern hemisphere of the sky locally. We think of SWIRE as the Sloan of the higher redshift universe, and we'll be able to directly compare the structures seen at those higher redshifts in SWIRE to the local universe and see how they have changed in time.
By gazing into the deepest reaches of space-time and revealing millions of distant galaxies, SWIRE will help us unravel the cosmic web.
Lyman Spitzer was an inspiration not just as a scientist, but in addition to that, he was really a remarkable human being.
He was a visionary, he was a scientific leader. He was the one that in the 1940s, before anybody could ever imagine putting a telescope in space, he immediately started thinking and he said, well, there are rockets, we can go above the Earth's atmosphere. Why don't we build some mission, put a telescope up above the Earth's atmosphere?
So he wrote this paper for the Rand Corporation. It was an unusual proposition that he was making. If you could get away from the atmosphere, which makes the stars twinkle, which is very pretty and romantic and all that, if you could get above that and get a telescope up there, you could learn a good deal.
People thought he was crazy. It just sounded like science fiction.
He did some early work on balloon measurements to show how great was the improvement if you got to greater heights. And as a result of that, Lyman became the focal point for putting telescopes in space. Anybody that studies astronomy and astrophysics has to think of Lyman as a great pioneer, but also one who laid the foundations, solid foundations for future work. He made epochal contributions in plasma physics, in stellar dynamics, in space physics, in the interstellar medium, and how stars form.
I think it's fair to say that if any one person created the field of thought of interstellar astrophysics, it was Lyman Spitzer. He was certainly among the very first people to be applying laws of physics to thinking about interstellar dust and recognizing it as something which was not just the annoying obscuration which bothers optical astronomers who'd be quite happy if there simply were no interstellar dust, but rather he recognized that it was something which was a crucial constituent of the interstellar medium.
The last of the great observatories is up and running now. It fits what Lyman Spitzer's vision was perfectly well, and that's why I'm so sorry he's not here to see his dream come true.
His outlet was rock climbing.
He was a very good climber, took probably a few more risks than I would have been willing to take. When he was chair of the department and was quite senior at the university, he decided it would be nice to climb the tower of the graduate college. He thought, well, the worst thing they could do is take away his chairmanship of the department, which he thought was perfectly okay. So he completed the climbs and was reprimanded and I guess went home.
The students just adored him.
He had this aura and presence when he walked in a room. You knew you were in the presence of a great man, but he did not want to take any of the credit away from the young people that were working with him.
His office was in the house, at the foot of the stairs. The kids would want to come in and he would drop whatever he was doing, and it was always time for his family. He loved his family. He was a pocket of clarity.
Bright, innovative, very gentlemanlike.
He was a sufficiently powerful personality with enough good ideas that most of those ideas have lasted until now.
Spitzer's legacy, I would say, is the achievement we have obtained with the great observatories is just unparalleled. What Lyman Spitzer's achieved with his dream is comparable to what Galileo has achieved in revolutionizing our understanding of our universe.